First, I want to thank organizers for organizing this workshop and give me this opportunity to share my recent work to you. So my talk is about vector meson spin alignment. So this is the outline. I will first quick review the global polarization and the global spin alignment of vector mesons. And then I will turn to azimuthal angle dependence of the lambda polarization, which is also known as the local lambda polarization. Then I will talk about the local spin alignment of vector mesons, and that part is based on my recent work, which is in collaboration with Hui Li, Xu Guanghuang, and Huan Zhonghuang. And our paper is going to be appear on arXiv tomorrow. And then I will give a summary.
Hi, Xiao-Liang.
Hi.
It's not clear. Your screen is not clear. I don't know why.
I have no problem on my side. Is it?
Oh, okay. I will try. It's maybe my problem. Okay.
Okay.
Sorry.
Okay. So as we know that in heavy collision, in non-central heavy collisions, there is a huge orbital momentum, and such an OAM can be partially transferred to the spin polarization of particles in the system, and this can lead to the so-called global polarization. And as you know, STAR has measured the global lambda polarization, and you know about this story, and experiment data can agree with the theoretical calculations by different approaches. And in addition to the lambda polarization, another particle, the vector mesons, can also be used to study the connection between system rotation and particle spin. So let us consider vector mesons which are produced by quark combination. So vector mesons are a particle of spin 1, so it has 3 spin states along a specific direction. And the spin state of vector mesons is given by the spin triplet state of quark and anti-quark. So following the idea of the global polarization, quarks and anti-quarks are globally polarized. Then, because polarization means that there are there is a larger number of spin up particle than that of spin down particles. So the vector mesons produced from quark combination will have different probabilities to occupy the 3 spin states. So from the polarization of quarks and anti-quarks, and calculate the probabilities, one can obtain the spin density matrix of the vector meson given by this equation. This equation has been derived from Yin, Liang, and Wang's paper. And among the 3 diagonal elements, only rho 0, 0 is measurable in experiments. So using the formula in the previous page, we can do some quick analysis. So if the polarization is induced by the global orbital angular momentum or the global vorticity, then quarks and anti-quarks are polarized along the same direction. So according to this equation, rho 0, 0 will be smaller than 1/3. But on the other hand, if quarks and anti-quarks have opposite electric charge and the spin polarization is caused by magnetic field, then the spin will along the opposite direction. This can also be caused by vector meson field or quark fragmentation. So in this case, quarks and anti-quarks are polarized along opposite directions. Then according to this equation, rho 0, 0 will be larger than 1/3. But in both the cases, rho 0, 0 is not equal to 1/3. That is expected to signal the non-trivial global polarization of quarks and anti-quarks. And Star and Alice have measured rho 00 for K star and phi meson, and Takafumi also showed these results in his talk. In a short conclusion is that rho 00 and for K star and phi indeed deviates from 1/3 in a wide range of centrality. But the unexpectedly large magnitude has not been understood. So in the analysis in previous pages, people always assume that particles are polarized globally along a specific direction. In the case of the global polarization, that direction is the OAM direction. However, we know that the global polarization, the global OAM is not the only source of vorticity and consequently the polarization. In fact, there is local vorticity in which particles are locally polarized. So in non-central collisions, the elliptic flow V2 can produce a quadrupole pattern of the longitudinal vorticity on the transverse plane, which is illustrated by this picture. And if there is V2, then partial x Vy and partial y Vx cannot be equal. So there is non-zero omega z. And in such a vorticity field, particles are polarized locally, and particles will have longitudinal polarization. And from the symmetry of the system, geometry system, Pz can be written by this equation. And as you know, there is a puzzle regarding the opposite sign between experiment data and theoretical predictions. But although there is a puzzle, the existence of the local longitudinal polarization has been evidenced. Besides the longitudinal polarization, the longitudinal polarization is in non-central collisions, but in both central and non-central collisions, the gradient of radial flow along the z-axis can generate transverse vorticity loops at finite rapidity, which is illustrated by this picture. So because the fireball is not uniformly distributed along the longitudinal direction, so its transverse expansion will have a gradient along the z direction. So it can generate transverse vorticity given by this equation. Here, E phi is the azimuthal direction that circling around the z direction. And such the vorticity pattern has been observed in different model calculations. In this page, I showed some examples. So if you observe this transverse vorticity on the xz plane, which is the reaction plane, then you will see the quadrupole pattern of omega z component given by this picture and this picture. And if you look, if you observe the 3D distribution of this transverse vorticity, then you will observe the vorticity loop given by this picture and this picture. So in such vorticity pattern, there will be transverse local polarization, and the polarization px and py is along E phi direction. So it is sine azimuthal angle and cosine azimuthal angle. And this is the model calculation using MPT for px and py, which you can see is sine and cosine modulations. And so up to the leading harmonic in Fourier series, the polarization vector can be written as this equation, and here P global is the global polarization, and Fx and Fy is the transverse local polarization, and Fz is the longitudinal polarization. Here in this equations, it mainly includes the contribution of vorticity, but if there is other sources of polarization, such as magnetic field, maybe this equation should be modified. And we have studied the centrality dependence of the local polarization. So using the MPT model, we calculate how large is the Fx, Fy, and Fz. And you can see from this picture, in central collisions, the global polarization and Fz, which is from V2, is 0. And in the most central collision, Fx and Fy are equal because in the most central collision, there is a rotational symmetry around the z direction. So Fx and Fy should be equal. And in non-central collisions, we know the global polarization is not 0, and the longitudinal local polarization Fz is not 0 too. And there is a difference between Fx and Fy, but in all the cases, we say that the value of x and Fy is much larger than Fx and the difference between Fx and Fy. This is because Fz is generated from V2, so which is small, but Fx and Fy are generated from radial flow, which is always large. So we have known that particles are locally polarized in QGP, and those local polarizations are consequence of the bulk geometry of the QGP fireball. Therefore, after average over many events, the local polarization can survive. So then it is, we should ask the question, what is the effect of such kind of local polarization on the spin element? So to study this question, let us first recall the global spin element. In the global spin element, as I said, people assume that particles are globally polarized along the OAM direction, and in this picture is the y direction. So the vector, the polarization vector for quark and anti-quark has only one non-zero component, is Py. In this case, the density matrix for quark and anti-quark is a diagonal element matrix given by this. Then to obtain the vector Mason spin density matrix, people first make a direction product between rho Q and rho Q bar, and then translate the results to the spin turbulent state. Then one can obtain the spin density matrix for the vector Mason given by this equation. And we say in case that P has only Py component, the spin density matrix is a diagonal matrix. However, in the local spin element illustrated by this picture, quarks and antiquarks are possible to polarize along any directions. So the polarization vector has 3 non-zero components, and the off-diagonal elements are non-zero. So using the same method in the previous page, one can obtain the spin density matrix for vector Mason from the spin density matrix for quark and antiquark, and the result is written down here. So these results are complicated, and we have some comments here. So first, let us look at the row 0, 0. We see that it does not only receive contribution from PY, but also from PX and PZ. You can see here. And in the presence of PX and PZ, the off-diagonal elements of row V are non-zero, so they are here. But those contribution of PX and PZ is not included in the studies on the global spin alignment. So in the experiment, the spin information of vector mesons is extracted from the angular distribution of the decay products in the strong decays. The angular distribution is given by this equation. Here, theta is the angle between the decay product and the y direction, and the phi star is the angle between the projection of P in ZX plane and Z axis. And by measuring this angular distribution, one is able to extract 5 coefficients from this distribution. And according to our results for spin density matrix, these 5 coefficients are related to the quark polarization given by these 5 equations. And by the way, from the equation for spin density matrix of the vector meson, one can also obtain the relation between quark vector meson polarization and the quark polarization. However, the polarization vector is not measurable in this angular distribution. Then let us study the local spin alignment. So as we know that in non-central collisions, the polarization of quarks and antiquarks is given by these equations. And from our numerical calculation, we know that in the above equations, Fx and Fy may dominate over the global polarization and Fz. And in the most central collisions, there is a rotational symmetry around the z-axis. In this case, the global polarization and Fz is exactly 0, and Fx and Fy are equal. So the polarization for quarks and antiquarks is simpler given by these equations. Then let us discuss what will happen to the spin alignment if the quark polarization is like this picture. So we know that the rho 0, 0 is determined by quark polarization given by this equation, and the quark polarization in this picture is described by these equations. So we insert this equation into the rho 0, 0, and we find that rho 0, 0 depends on this azimuthal angle by this equation. And we find that this kind of local polarization can lead to rho 0, 0 to deviate from 1/3, and also because the local polarization oscillates in delta psi, there is also harmonic oscillation in rho 0, 0. So then let us explain why rho 0, 0 oscillates in this way. So at azimuthal angle equals 0, which is here, quarks and antiquarks are polarized in the y direction. So according to this equation, rho 0, 0 is smaller than 1/3 because it is contributed by Py. And as this position is here, Px, the quark polarization is along x direction. So because rho 0, 0 is contributed by px, it is larger than 1/3. So
Excuse
therefore,
me, Xiao, but now there is this large bar which is really somehow annoying because it somehow.
I see.
Can you try to remove it again? Yeah.
It's
Oh, now it's
removed
better. Now it's better.
Okay.
Okay, thank you.
Okay. So the previous result is the delta set dependence of rho 0, 0. Now let us look at the average value of the rho 0, 0. So after integrating out the azimuthal angle, we find that the average value of rho 0, 0 is smaller than 1/3. So in this curve, the average value of this curve is not 1/3, but lower than 1/3, indicated by this purple curve, purple line. So this is a striking feature because in this quark polarization equations, the mean value of the average polarization of quarks and other quarks is 0. However, after average over the vector mesons, the average rho 0, 0 is smaller than 1/3. So to understand why is that, we can do a Taylor expansion to rho 0, 0. Then you can see that in this equation, Py contributes more to 0, 0 than Px and Pz because this coefficients is 2 times of this and this. So although in this quark polarization, Px and Py are equally weighted, in rho 0, 0 after taking average, it is smaller than 1/3. So we have shown you that both the global spin element in this picture and the local spin element in this picture, they can both cause rho 0, 0 deviate from 1/3. Then we should ask which scenario is dominant in heavy collisions, or in other words, if they both contribute, how to separate their contributions. Before the end of my talk, I wanted to discuss the difference between the global and the local spin elements. So the first difference is that although average value of rho 0, 0 is not deviated from 1/3 in both cases, the azimuthal angle dependence of rho 0, 0 is different. In the global spin element scenario, because particles are globally polarized along y direction, so rho 0, 0 is almost constancy. However, in the local spin element, I have shown you that rho 0, 0 will oscillate like this. And the second difference is that the global spin alignment, in the global spin alignment, the off-diagonal elements are 0. However, in the local spin elements, the off-diagonal elements are non-zero because there is Px and also Pz component. So this is a relation between off-diagonal elements and the quark polarization. And considering quark polarization is given by these equations, we found that this elements and this element are non-zero given by these equations. So what's the meaning of non-zero elements in the spin density matrix? The non-zero of diagonal elements indicates that the decay, the angular distribution of the vector meson decay has a non-trivial shape in phi star angle. Here, the phi star angle is an angle that circling around the y direction. So to understand this, let us look at the spin polarization here. Because in the local spin alignment, the spin polarization and here is along the y direction, And the spin and the angular distribution of the decay is looks like this, which do not depend on phi star, but for polarization at here and at here, it has non-zero components along x direction. So the angular distribution of the vector meson looks like this, and you can see that these two angular distribution has a non-trivial dependence on the phi star angle. The phi star angle is the angle that rotates around the y direction. Rotate around the y direction. So in the experiment, one can measure whether or not the angular distribution depends on phi star. And the third difference between global and local spin alignment is that one can study how does the rho 0, 0 average value changes with different choices of event plane, because in experiments, rho 0, 0 is determined by from the distribution of theta star, and one can define theta star with respect to different event planes and study how rho 0, 0 will change. And in this local spin alignment scenario, because this system has a rotation symmetry around z axis, so the local spin alignment is insensitive to rotation of the event plane around the z axis, which means rho 0, 0 will not change if you rotate the event plane in transverse plane. However, in the global spin alignment, if you rotate the event plane from zx plane to yz plane, then it looks like that the polarization direction is changed, is rotated. So the average value of rho 0, 0 minus 1/3 will flip its sign. So this difference can also be used to distinguish which scenario is dominant in experiments. So here comes to a summary. We have studied the spin alignment of vector mesons arising from locally polarized quarks and antiquarks. And we found that in addition to Py, rho 0, 0 also receives contribution from Px and Pz, but such contribution is not included in the previous studies on spin alignment. And we show you that rho 0, 0 deviate from 1/3 does not signal the global polarization. It may also originate from local polarization induced by local vorticity. And to separate the contribution from global polarization and local polarization, we propose to measure the azimuthal angle dependence of rho 0, 0, of diagonal elements in the spin dancing matrix, and rho 0, 0 with respect to different event plane. So these measurements can separate the local spin alignment from the global one and help us to better understand the local vorticity structure and the spin polarization phenomena in Hadron collisions. Thank you.
Thank you a lot. Thank you for being on time, even we have still more time than expected for discussion. So your talk is open now for discussion. Please raise your hands. Who wants to ask question? Oleg, please go ahead. Unmute your mic.
Yes, okay, thank you. Hello, everybody, and thank you for interesting talk. And I actually have maybe several comments. And first comment is that indeed, because the tensor polarization alignment is parity even, and vector polarization is parity odd, it's proportion. There is a term proportional to product or square of polarization. Absolutely true. But also it can emerge not due to product of polarization, but due to correlation of polarizations. And in fact, this equation containing product of polarization is valid if you substitute the product of polarization by correlation. And correlation may emerge either as a product, and this term is either as a product or correlation. And I suspect that basically your results are valid also if you substitute product by correlation. I think that your main conclusion that it can emerge due to local vorticity, somehow this is similar to the effect of correlation. But maybe the difference is that the local vorticity is still emerging as a sort of variant collective effect, but correlation can also emerge at the stage of fragmentation or formation of vector meson. And this is basically my first comment, that maybe it can be generalized not only for local vorticity, but for the case of just a correlation. And it's possible maybe to try to distinguish these two mechanisms, local vorticity and correlation. My second comment is due to magnetic field. Indeed, for magnetic field, it's a similar situation. One can have the effects due to product of polarization, but can have also effect of square of magnetic field. And it appears that we studied it with Yelena Lushevska and other just people on the lattice. And it appeared that longitudinal polarization with rho zero exceeding 1/3 is somehow similar to the conductivity emerging in the magnetic field. In fact, such a situation based on the effect of conductivity was even predicted. And my maybe third comment is related to the different components of density matrix. Indeed, it contains a rich information. And of course, this matrix element depends on the orientation of the axis of coordinate frame. And there are some invariants which do not change under the rotation. Now they are started to be used in the processing the data in hadronic collisions. Maybe it can be also useful here. This is my comment. Thanks.
Okay, thank you. So this was the comment. We have a very general question from Samapan Baduri, who is a PhD student. How do we determine which particles are suitable for measuring polarization in heavy ion collisions? Who would like to answer this general question? How do we determine which particles are, I can add most suitable for measuring polarization in heavy ion collisions? Student's question.
I would say, if possible, unstable particles who are somehow self-analyzing. For example, the lambda is self-analyzing and vector meson is self-analyzing. So this is the answer. I think one possibility of that. Otherwise, to measure the polarization of stable particle, one needs rescattering and so on. And for example, to measure the polarization of protons, it is very difficult problem, right?
Yeah. So first they have to have spin. Yeah. So that's kind of and then they should probably decay. So via decays, it's easy to analyze.
For the polarization vector, you need a decay with parity violation.
Exactly.
For the polarization vector.
It's extra. It's parity. If it is parity odd, you need. If it is vector which is parity odd, then you need parity violation in decay. Absolutely.
Okay, so there is a question from A Hong Tang.
All right. So you are saying one should look for the global rho 00 as a function with respect to the reaction plane to see if there's such what is called local polarization. But why don't you just take the circular line as your quantization axis say I take a particle's momentum cross the z direction and take that vector as my quantization axis. That in that sense, I would be measuring this, what you call local polarization directly.
That is the productive plan, right?
That is not a production plan. That is well, in that sense, every quantization axis is the cross product of the particles. I shouldn't say it's momentum. It's you know the PT, right? You know the PT cross the Z. That will give you those little blue arrows. You take that as your quantization axis, then you will be measuring the what you call the local polarization. You know,
yes.
you have a PT vector, then you cross product that with Z, that give you little blue arrow. Then you measure that directly. If you see a finite value, that's your local polarization.
Okay, guys, so I think you have to discuss it privately, maybe more, or we can discuss it during the roundtable discussion. There is another question from Hong. Okay, disappear. Hong E.
Yes.
Hong
Yeah,
E. Okay, please. Sorry for wrong pronunciation.
Could you go to slide 23? I have a question about this. This number of particles as a function of angle. How robust is this formula? Is it based on some kind of a microscopic quark model picture, or it is more or less dictated by the symmetry of
It's
problem?
by the symmetry.
It's completely fixed by symmetry.
Yes.
I see. So then what? Why does it matter? Is a strong decay or weak decay? Does it matter, or?
Because those mechanisms, they strong decays.
Okay.
They do not weak decay. Yeah.
Yeah. Thanks. Yeah.
Okay, I don't see any further questions here. No. Oh, I see. Francesco wants to join. Okay, Francesco, go ahead, please.
Can you hear me?
Yes.
Yes, yes.
Can you go to slide number 36? Yes. So I was wondering about the symmetry and this picture. So that on the panel B, so you have polarized. So are those quarks polarized, say, in the with this curl pattern? So is the arrow the spin of the quark?
It's a spin of quark.
Okay. So I was wondering about the symmetry of this picture. So in other words, if this is y the direction of the angular momentum, or and xy, say, the transverse plane?
XY is the transverse plane. Yes.
Yes. So, but if you have, for instance, but this picture does not. So maybe I misunderstood, but this picture seems not to fulfill the rotational symmetry in a sense. Rotational, I mean, around the angular momentum axis.
The rotation is around the z-axis.
Only in central collisions, right?
Oh yeah, only central collisions.
But you also have a rotational symmetry of 180 degrees around the angular momentum.
Not around angular momentum. The rotation symmetry is.
You should have a rotational symmetry of 180 degrees around the angular momentum axis.
Okay. Well, yeah. Okay.
Okay. So but in this picture, you don't have that, because if you rotate.
Okay, I see. To make it clear,
Yeah,
you know,
okay.
this picture is rapidity out.
Okay.
Okay, it's all rapidity out. So this picture is at a positive rapidity. Let's see.
Okay. So this is rapidity. It's not zero rapidity. Okay, I see. Okay.
Okay, yeah.